Okay. So let me kind of paint the situation for you. We've really been focusing on conservation of momentum, and I'm going to refer to it as linear momentum, only because in chapter 12, you're going to be introduced to another flavor of momentum, and so I'm just starting to distinguish linear from this other type, which I'm not even going to worry about now. So imagine this situation where we've got a couple of carts. They're different, 5 kilograms, 2 kilograms. They're moving head-on on a track, kind of like this thing. I just set up a little visual for you here. So different masses, different speeds, different directions. And so if we only think about, okay, momentum has to be conserved, we would have no way to know what happens. So here's a conservation of momentum equation that would apply. I've not written out symbolically here. I've just written it with actual numbers from these. I was careful to include the negative sign because this guy's moving leftward, so that translates into a minus sign when we do one-dimensional stuff. So here's the equation using all the initial information. And so can you tell, just based on the way I wrote it, why you could not predict with certainty what will happen after the collision?
Yes. Because the forces are balanced out, so it wouldn't. Well, okay.
We don't have any of the final speeds.
Okay, but I mean, there's got to be some final speeds we should be able to put in there, right?
I mean, they could go either way.
Okay.
The momentum is the same at the end.
Well, the total momentum is the same as this. And what is that number? That's, I can do math, right?
20 plus
20 plus minus 6. Okay, so we're looking for 14? 14 units of momentum. I'm not writing units down. So, if I gave you enough time, could you think of a set of numbers that we could put here so that the total of that was 14?
Yeah.
How many different sets of numbers do you think you could come up with?
Well, like an infinite amount.
An infinite number of them would actually work. A lot of them would be absurd, but there are an infinite number of values we could put here. You know, if we made this one big enough, we could make this one, you know, small enough or whatever. We could have two positives. We could have a really big positive with a negative, as long as it totaled up to 14. So we would refer to this as like indeterminate. But that's impossible. That can't be. Like, we can't have two things crash together and then just like different things happen different times. So there's got to be, in physics, the idea is there ought to be predictability. So it turns out there are different things that can happen, but it's not random. It's dependent on, essentially, what you're crashing together. So if we use two identical carts, and you've only used one of them, so you wouldn't have known this, but there are inside here interesting things. Watch, this is very visual. And I know that on the video we're not capturing this. Sorry, I had the wrong cart. So these are two different carts. You see what's on there? You can hear it. That's just Velcro. Hook and loop. I replaced the wrong thing. But if I choose two identical carts,
We got magnets.
there are hidden magnets in there. Whoops. They have to line up. If they don't line up, it doesn't work. So, that was just for your amusement there. So it really depends on, you know, what we put in there. So if we put something sticky, like, well, Velcro's fun, but like peanut butter. Well, no, this is.
What?
Yeah, peanut butter. Yeah.
Who does
What's wrong?
If we use something like Velcro, where it sticks together, there is a name for that kind of collision.
Sticky.
Inelastic is the physics name. Sticky is okay. Because that really describes what happens. They stick together. But if we use magnets, then we have another type of collision known as,
The last one.
right, in fact, this is what we call completely, can't remember, I think there's an E there, elastic. So that would be something like magnets or springs. But most real collisions don't have those. I mean, your cars, when they collide, they don't have Velcro, they don't have magnets in them. And so you get a little bit of crumpling, and so it would be categorized as like partially elastic. Again, most collisions are that way. So, with the completely inelastic one, you could predict, I made the numbers such that you could probably do this in your head. Remember, we're starting with 14 units of momentum. And so if we have them combined together, total of 7 kilograms of mass now moving, what speed would they have to go, with what speed would they have to move with in order to have 14 units? That would be 2. Now, this one, if I give you one of the speeds, you could predict the other. This reminds me of the quiz. Question 2, maybe? The question, I don't know, one of the questions. So can you figure out what... Don't blurt it out. Just ponder for a minute. Again, trying to keep the numbers, things you can do in your head without a calculator. 17 seconds to come up with that velocity there. Kind of giving it away in that it does move that way. All right, blurt it out if you know it. Got to be 1 meter per second. Because this guy has 9 units of the momentum, and we need 5 more to make the total of 14. So that's where we get the other 5. Now, here's an interesting problem that I have not had you do because it's a pain. But if it's completely elastic, there's another conservation law that applies. In physics, completely elastic means all the kinetic energy we start with, we also end with. So this equation that was indeterminate because we really had 2 unknowns with an infinite number of solutions suddenly becomes 1 solution if we write another equation with those same 2 unknowns. And it's not anything, it's messy, but it's not anything that would be difficult to write. Trying to use color here. So if conservation of kinetic energy means all the kinetic energy we start with, which is 1/2 mv squared for each one. So there's the red cart's energy, and then we'll add in the blue cart's energy, this kinetic energy again. I am not putting a minus sign on this because we're going to square it anyway. And for some reason, those fancy calculators of yours, if you put the minus sign in there and then square it, it'll give you the negative number. It drives me bananas, but I didn't make the calculator, so there's not much I can do about it. So whatever that number is, if somebody doesn't mind while I'm finishing writing, can you figure out what that number is? Just add those up. I'm not sure it's doable in your head. There's a reason I didn't do that one.
9.
Is it? Okay. Let's have 2 people do it so that we can.
I forgot the first number. I think it's 21. No,
Yeah, this is why somebody else also needs to verify. No offense, Roy, but
Yeah.
it's always good to have somebody checking in.
80?
I got 49.
13.
With my
Oh, with your calculator, I trust. 49 sound okay? I think you're right. I think it is 49. 49 units, this time I'll write joules. I hate writing momentum units. They're so long. I don't like them. There's no abbreviated momentum units. So yeah, this is 16 times 2.
Oh, yeah. Yeah, it's 16 times.
Yeah, it is 40.
Oh yeah. Monday morning mental math. Probably not a good combination.
16 times 5 is 80.
Okay. All right. Yeah.
150.
40 and 9 more. Okay. The 9 part's easy. I wasn't sure about the 40. Okay. So, do you agree, and this is what Algebra 1 or Algebra 2, they teach you that if you have 2 equations with the same 2 unknowns, that you will get a solution. A single, an ordered pair solution. Or on graphs, it's the intersection of the graphs,
Yeah.
right?
You had to do like a substitution.
I always did it with
It's
substitution.
not algebra.
Because I'm not lying, and when I was in high school, we didn't have graphing calculators. We didn't have calculators.
Yeah, but now we can graph it.
So now you can graph it and find the intersection. That's not so bad.
We love Desmos.
Or, yeah, Desmos is great. Or, those fancy calculators of yours have, I think a lot of them have these solvers on them, where you just type it in like this, and hit go. And it'll...
They do, yeah.
What?
Yeah.
Now, if you don't have any of that, or you don't know how to use it, you go to the internet, and you Google in completely elastic collision equation, and you find it there, and they're ugly. I'm going to show you how ugly. Oh man. Ready for this? So, essentially, if you do substitution, solve for one of these unknowns, plug it into the other, it's a mess. Here's what you get. V5 final and V2 final. I'm not going to write all this, but I will. Okay, V2 final is 2 times 5 kilograms over 2 plus 5 kilograms minus 5 minus 2 kilograms over 2 plus 5 kilograms. So there's the final velocity for the little guy. And then the final velocity for 5, I'll write it in red to be consistent. Again, I'm skipping a whole bunch of algebra steps that you wouldn't want to see anyway. Is 5 minus 2 kilograms over 5 plus 2 kilograms times V1, which is... Oh, I messed up. There's already a problem here.
What?
Yo.
I missed the speed. I gotta put the speed in. The initial speeds kind of matter.
Yeah. Speed.
All right. Plus 2 M2.
You are.
2.
You are an idiot. Yep.
Yeah.
I really just beat you. Here. No, not if you can block it. Yeah, if you start in the right spot.
All right, there they are.
Yeah, if you lost.
So these 2 equations, when algebrated and substituted, and that's a lot of work, will give you that. And I've actually plugged the numbers in rather than left it symbolic. I was kind of impressed with myself. I literally made these numbers up just to keep the numbers nice. And it turns out that this guy, when I plug it in, again, I will be plugging that in here. This isn't so bad. This is 10 times 4, that's 40 over 7, minus 3 times negative 3 is 9 over 7.
49 over 7. 49 over
49 over 7, yeah. So it came out a whole number. I did not expect that. Turns out this one moves at 7 meters per second that way, which is surprisingly fast maybe, but this is 2.5 times as massive. You'd be like this big truck slamming into this little guy and just... Wrong cart. the elastic one. And so it really kicks it back. Well, here's what's interesting. Calculate the kinetic energy of just the second one, now that we know how fast it's moving. Again, you can do that in your head. 1/2 m times that squared.
0.
Wait, no, this guy.
Oh.
I know what you were.
149.
It's 49, which is the total energy we started with. So that means the other one can't have any. It's actually stopped. Again, kind of a fluke that I happened to pick that pair, but it works. So that is, we would call that determinate, like there is a solution. And it has to happen that way every time. If we have good magnets and we have the right ratio of masses and the right ratio of speeds, it will always make the one stop. Kind of neat. So, but that is a combination of two conservation laws kind of working together. Again, I've avoided all the ugly algebra. If you want to watch somebody do it, then you can go to YouTube and find people that love to impress with their algebra skills. I'm not one of them. No. We tend to, like, I always joke, go find a math major to do that for you. We just need the physics. You just have to know what to apply.
They know the card math, they know the algebra.
Yeah. So, again, this is a little artificial. It's hard to make this happen without lab equipment. Hard to make that happen, which is why, in reality, something different happens and it does end up kind of unpredictable. Okay. So, all right. Well, it was longer than I usually spend, but, oh golly, that was 16 minutes. 16 minutes.